Now, what I think is really cool is that we can undo, well, not undo DeMoivre's theorem, where he taught us how to take a complex number in polar form and raise it to a power. We can reverse that and look for the roots of a complex number in polar form. Now, one thing that's kind of interesting about roots of a complex number in polar form is that it has two distinct roots. It also has three distinct roots. It has four distinct roots. Wait for it. It also has five distinct roots, and so forth and so forth and so forth. So that you can look at any complex number and choose how many roots that you want to focus in on. The two equations that we can use to do that, notice that they're both similar. One is in radians and one is in degrees, and where n represents the focus that we're looking at, what root that we want to do. And then our k's, if there's four roots, we're going to be looking for four options. So k will begin with 0 as being our first one, 1, 2, and so forth until we get down to 4 minus 1, which is 3. So in this particular case, I want to look for the fourth roots of this particular complex number written in polar form. So let me show you how I would do that. So the first one I'm just going to look for is z sub 0. So that's where my k is 0 in this particular case. That's going to equal the fourth root of 16 times the cosine of 120 plus 360 times 0 plus I times sine of the same material. That's going to be the same. The arguments are going to be the same in both of those. So just for the sake of space, I'm just going to have an empty parentheses there. And this is divided by 4. Likewise, that's divided by 4 too. I want to make sure I do that. So let's clean that up. The fourth root of 16 is a 2. Cosine of 120 plus 360 times 0, so it's just the 120. 120 divided by 4 is 30 degrees, plus I sine 30. So there is our first root of this complex number when we're focusing on looking for 4 of them. So let's look for the next one. So just as an organizational matter, z sub 1 is our next one we're going to look at. So that helps us to go to the fourth root of 16 times the cosine of 120 plus 360. Since this is my first one, that's a times of 1 now. Let's make it a bigger one because you guys are playing along at home. Plus I times sine of the same argument. Let's clean that up a little bit. Fourth root of 16, we've already discovered is a 2. Cosine, oh, I always forget, that's divided by n. 120 plus 360 is 480. 480 divided by 4 is 120. Plus I sine of 120. So there we were able to find out all the different ones that we have. That's, well, not all the ones. That's the second one that we were able to discover. From there, let's go ahead and do the next two. So z sub 2 and z sub 3. And again, for sake of space, I'm just going to write those in there. Notice that z sub 2, rather than putting a 0 or a 1, I'll put a 2 in it. And that resolves down to 2 cosine 210 degrees plus I sine of 210 degrees. And the third root, or sorry, the fourth root that I'm looking for is going to be 2 times the cosine. I'll put 4 in this spot, multiply it through, so that'd be 120 plus 360 times 4 divided by 4 produces 300. Now, I understand if I skipped ahead on that second and third one, and you're still a little foggy, it's like, how did I know it was 210 degrees or 300 degrees? That's just, I was going through and just adding up and doing the stuff inside the argument. So you can verify that on yourself. There was no magic there, no smoke and mirrors. So don't let that throw you. So we found 4 distinct roots of this original complex number written in polar form. And then graphically, what that means then, that if I were to kind of draw a unit circle or so, I would have the first one at first point at 30 degrees, 2 units out. So I kind of have a, and then on that unit circle, and I'm going to use a whole bunch of different colors here. Cosine of 30, or angle of 30 degrees, puts me right about there. So that's the location of one distinct root. The next location is at 120 degrees. The next one, the z sub 2, that's at 210 degrees. Right there on that unit circle with a radius of 2 degrees or 2 out. And then the last one is at 300 degrees. And so that's how we would represent the 4 distinct roots of this complex number written in polar form. 4 roots, and these roots are equally spaced around the circle. If we were looking for 3 roots, we would find 3 roots on the circle, evenly spaced around the circle. 5 roots, we would find 5 roots, evenly spaced around the circle. We just happen to focus on 4 roots of this particular one, but we could have focused on any other one that we wanted to. And because we can, and we're having fun and all those types of things, let's figure out what we can do and how to find the cube roots of 8. We need to think about this in terms of our complex plane. We're going to use our friend DeMoivre's theorem backwards to help us figure out how to find the cube roots of 8. Well, first of all, we need to think about 8 in terms of the complex number. So it's 8, or it also equals 8 plus 0i. We need to convert that to polar form. Polar form, again, was r times cosine theta, I sine theta. And so if you did your work, that's going to equal 8 times the cosine of 0 plus I times the sine of 0. And that's using if we remember, that's using our r equals a squared plus b squared over c, and the tangent of theta equals b over a. So just using those two produced an r of 8 and a theta of 0. All right, so now we rewrote 8, which is a nice, simple, clean number, into what appears to be a more complex form in polar form. But it's in polar form, which now allows us to think about how do we work with this. We can choose either radians or degrees. Let's do radians because we did degrees last time. So I'm asking for then, we're looking for the cube root, and there's 3 cube roots. So z sub 0 will be on my first one, and that's going to equal the cube root of 8 times the cosine of 0 plus 2 pi times 0, since that's my first one, all divided by 3, plus I times the sine of theta, or sine of the same argument. And then cleaning that up a little bit, the cube root of 8 is a 2. Cosine of 0 plus 0 divided by 3 is a cosine of 0. Plus I sine of 0, which equals cosine of 0 is 1. So that's 2 times 1 plus I times 0, which just equals a 2. All right, that's our first location that we have. That's our location of our first root that we discovered. Let's look for another root. So at the first iteration, 3 cube root of 8 times the cosine of 0 plus 2 pi times 1 this time, divide by 3, plus I sine of the same argument, 2 times the cosine of 2/3 pi, plus I times sine of 2/3 pi, 2 cosine of 2/3 pi is, it's on the second quadrant, cosines are negative right there, so that's a -1/2, plus I times the sine of 2/3 pi is a positive, whoops, let's put that outside there, is a positive √3/2. And then cleaning that up a little bit, 2 times -1/2 is a -1. 2 times that gives me a plus an I. Sine of 3/2, oh sorry, sine is gone, it's √3, that becomes I √3. The sine of 2/3 pi is √3/2. All right, there's our second point that we're able to find. And then our last point, since we're looking for 3 roots, this is my third go around. 2, whoops, sorry, √3 √8. Got ahead of myself. Times the cosine of 0 plus 2 pi times 2, all divided by 3, plus I times sine of the same argument. Cleaning that up, that's going to be a 2 cosine of 0 plus 2 pi, that's 4/3 pi this time. Oh, I lost my cosine, plus I times the sine of 4/3 pi. Cosine of 4/3 pi is a -1/2. And the sine of 4/3 pi is a -√3/2. Multiply that 2 through, that gives me a -1 minus an I √3. There's my third root, there's my second root, and here's my third root. So I found all 3 roots of 8 in our complex plane. And then graphically what those kind of look like. Let's go over here and see if you guys can see. There's my complex plane. The first one's over here at 2. The next one is over at -1 √3 up on the 2-unit circle. And the other one's over -1/2 down on I √3. All those are equal distance from the origin or from the pole. And if I did my radiuses right, those are all 2 units away from the origin as well. So those are the 3 distinct cube roots of 8 in the complex plane. They're equal distance from the origin or from the pole, but also too, they're equal distance from each other around the circle. All right, you guys all right with that? All right, maybe, maybe not. Well, do a couple practices, come back, watch me again, and we'll do it all over again.